Good afternoon, everybody. Tim Noka from ProTech. I appreciate you all attending our webinar today. Good morning to any of you that are west of the Eastern Standard Time, where we are located. Today's webinar is Software Testing for Machine Learning, hosted by Rod Davison. He's the smart guy in the room. I'd just like to take a moment or two for some introductory things. As far as questions are concerned, please don't hesitate to ask any questions during the webinar. Put them into the question area, and at the end of the webinar, after Rod is done with all of the slides and all of the presentation, we will go through any questions that came up, and Rod and I will stay to provide any answers. This is the latest in a webinar series that ProTech runs. All of our webinars, past and future, are off of our resource page on our website. Rod Davison has been working in the industry for quite a few years. He's got 10 years in civil engineering, testing models and methods, total quality management, and QA in industrial developments. Rod also has 30 years experience working in social science research and testing, with 10 of those being in medical testing, 30 years in software testing and quality assurance, 10 years working in market research, building testing models, and he's been working in AI since 1984. So Rod is looking forward to presenting today's topic on software testing in regards to machine learning. Rod, we appreciate your time, and everybody, we appreciate your attendance. There you go, Rod.
Thank you very much, Tim. The first thing I'd like to do is welcome everybody to this webinar. And I also want to point out that Tim has mentioned some of my background, and I need to point out that was all relatively concurrent. I didn't do it sequentially, otherwise I'd be about 200 years old. But for about a 30-year period there, I had my finger in many testing pies. I was trained as a mathematician, so I was helping civil engineers building testing models, predictive testing models, and also working in experimental psychology, which was overlapping with a lot of medical testing that was being done at the time too, and working with building experimental models, test validation there, plus in market research, building predictive models of human behavior with things like psychographics and other kinds of consumer prediction mechanisms. I started working in artificial intelligence in the 1980s, so I have a long relationship with the field, as with testing. I was an early adopter of software testing and quality assurance while I was working in artificial intelligence, as we definitely faced issues about how do we test the things that we're building. So today's seminar is going to cover a couple of different topics. First of all, we're going to look for the reason we need to do testing in QA and machine learning. The second thing we're going to look at is we're not going to go deep into software testing, but we are going to look at an interesting idea that Boris Speiser, one of the great gurus of software testing, pointed out, is that the field has been evolving. And this is a cusp point at which we are going to have to evolve the field again. Because the third point we're going to look at is, why can't we test machine learning right now? I mean, why can't we just test it the same way we test everything else? And then what we're going to do is to say, well, we can't, but we can now evolve software testing in order to now meet this particular challenge. So the first thing we want to look at is, why do we even need to test machine learning applications? And the answer is a weird phenomenon that takes place, and we see it everywhere with things like airline travel and other kinds of industries. It's called a confirmation bias. And it's where people cherry pick the events and facts to meet their preconceptions, or they just distort their point of view. So, for example, a lot of people say, oh, I don't want to fly, it's so dangerous, but yet they look at the statistics and see it's a lot safer than car travel. But the problem is their bias is being formed because all the safe flights don't make the news, it's the air crashes that make the news. And we find the same thing with machine learning. So, for example, IBM Watson developed this supercomputer cancer treatment machine learning system, and it was rolled out to a number of hospitals for its field evaluations. And you could see one of the doctors there had a fairly unkind thing to say about it and pointed out, by the way, this is 2013, pointed out that some of the recommendations the system made could cause severe and even fatal consequences. So doctors basically said, we're not using it. And IBM, of course, had to downsize the project and lay people off. So that is kind of a black eye in the field. Amazon had a black eye as well. They rolled out into production a recruiting AI recruiting engine, which is a machine learning model they had built. And as you can see there in the second paragraph, they said, what we want is an engine that's good. When we give it 100 resumes, it'll spit out the top 5 so that we can actually get the best people in the job. But as it turns out, the system was not ranking candidates for developer jobs in a gender-neutral way. The problem is that it was biased towards males. It was misogynistic because the data it had been trained on reflected the fact that over the last 10 years, the field had been dominated by men. This is the same thing, too. When we look at the Watson, when we ask the question, why did it happen? One of the reasons it happened was they didn't train the model on real data. They trained it on what they called hypothetical data, where they would ask doctors, what would happen if? And that's the data they trained it on, which was not the same as real data. So we've got 2 problems here that didn't get picked up until we got into production. Here's another interesting one, where this is, again, a commercial product which has been released into production, and they wanted to have something that would prioritize CVs. But before the client purchased it, they wanted to say, well, how is it doing this? What's the algorithm it's using? And they discovered that the tool was deciding that you're most likely to have job success if your name was Jared and you played high school lacrosse. That was a bit embarrassing because that just isn't the case. There may have been a correlation there, but it wasn't necessarily something that you would base a hiring decision on. Facial recognition gets in the news a lot. Facial recognition, we see it all the time on Facebook and all of these other venues. But the problem is that when we roll it out into the field, as we did in, not we, but as the MTA did in New York, they decided to use facial recognition to identify people at RFK. And as you can see in yellow, it says the initial period for proof of concept testing at RFK for facial recognition has been completed and failed with 0% faces being detected within acceptable parameters. It's pretty hard to fail a test more than getting everything wrong. Okay, so now that gives facial recognition a bit of a black eye. Well, okay, maybe that was a statistical fluke. Maybe that, that was the only one that did it. But England, which has this massive network of closed-circuit TV cameras, decided they were going to use facial recognition to identify bad guys, criminals, wandering around the streets of England and Birmingham and London. And as a result of their trials, they had a 96% failure rate in identifying criminals. In other words, 96% of the people identified as criminals weren't. And as you can see from the headline there, a 14-year-old black schoolboy was among those wrongly fingerprinted after being misidentified. One of the problems we have with facial recognition is that it's trained on white male faces generally, and so it has a very high failure rate on women and people of color when deployed out into the field. I'll notice all 3 of these are sharing some common characteristics. One of them is that the sample is not necessarily representative of the population where we're deploying the actual machine learning application. And this starts to show up, so we fail in that particular environment. Now, why is this a concern to us in the industry? Because this is a confirmation bias. It's the same thing that people point to these things and say, oh my gosh, this is going to be terrible. It's going to destroy our society. Look at all of these people we're going to throw in jail, these innocent people. Now, legitimately, there have been people who basically had their lives ruined by being incorrectly identified in facial recognition as criminals. But when you look at it, the thing that we've got to be concerned about as an industry is that we've reached this inflection point where major companies are being forced to take complaints seriously, and public dissatisfaction has reached such a fever pitch that some, including the city of San Francisco, are now considering all-out bans on facial recognition. And it's not just San Francisco, it's all over the place. So there's a lot of places they're saying, this stuff does not work in the field, so we're going to get rid of it. Now, it may work in the field, but it is these failure cases that are creating the public dialogue. But what about another field? Well, one of the things that Microsoft tried was to create this chatbot, which was a natural language processing system based on machine learning, and they put it on Twitter, so it was going to learn how to talk to people. And it actually was very successful from a technical point of view because it could carry on chats. The problem is that people, being the kinds of people they are, discovered it was like a little electronic parrot, and whatever you said, it would kind of incorporate. And it wound up being a misogynistic, racist, homophobic, genocidal psychopath in terms of what it was saying. I've reproduced one of the tweets there, and it's probably the only one I can show in public. The others are far too vile and offensive. And so after 24 hours, they basically had to cut the whole thing off. And oops, there we go. As you can see here, it is an avid supporter of genocide. So rolling these things out into the field creates an impression amongst often the general public, regulators, and other dimensions of industry and social segments and groups that machine learning is broken. So is it actually broken? The answer is no, it is not broken. And we know it's not broken because it works in so many contexts. For example, Queensland, Australia uses machine learning to do kind of predictive maintenance in order to protect their electrical grid. And it works incredibly well. They've had incredible success with this, reducing the costs, improving their efficiency. The field of biology has been using machine learning to start mapping genomes and global diversity. You can't do this manually. It's too complicated a problem, but with machine learning, you can create incredible kinds of results in your genomic analysis and looking at genetic diversity, not just with humans, but with other species as well. So if you want to look at the distributions of various kinds of strains of wheat, machine learning, again, provides an incredibly valuable tool. FinCEN, the guys that chase the bad money launderers in the U.S. government, use machine learning, and they do it very, very well. The problem they have is that people who are doing money laundering don't want to be caught, so they try to hide their crimes, but machine learning can sort of peel it back a little bit by looking for patterns that are actually there. So this is another example of something that's working quite well. And another final example is in medicine. Diabetic retinal neuropathy is a problem in India, but there's not enough people to be able to do the diagnosis, or because they take pictures of the retina and they analyze them. There's just not enough people to look at the pictures. What machine learning can do is flag pictures that are high priority or high probability of being images of people who need treatment. And so they can basically now serve a lot more people. So if we've got all these good examples and these bad examples, the question is what makes them different? And I'm going to suggest if we look at these fields of things like forensic accounting and electrical engineering, genetics and biology, medicine, these are fields which all have got a large depth of experience in testing various kinds of predictive and statistical models. And so for them, it's a natural thing to test. So that's one of the reasons why we see that machine learning in these areas seems to work in producing valuable applications that actually get results. So if it's not the machine learning that's broken, what is broken? And the answer to that is how we deploy machine learning into production. You notice when we go back and look at some of the examples I gave there with Tay and other things, the facial recognition, when we look back in retrospect, we can see the problem was, we used hypothetical data, not real data. We used data for facial recognition, which is biased towards white males. Our hiring data was biased towards men. In retrospect, we can look back and say, now we understand what the problem was. However, what we did was deployed it while that problem still existed, and it crashed and burned out in the field. In other words, some kind of QA or testing should have picked up those problems before it got into production. So that's what the problem actually is. Now, one of the great inspirations for this seminar is Chef Ramsay, because he made a very, very shrewd comment in one of his shows once. He said that when you run a restaurant, you have to be more than just a good cook. A restaurant is not just about good food. In our case, we could call those our machine learning models. It's also about the ambiance, the service, the consistency, the ability to get the job done, all the operational sides that are involved in running a restaurant that you don't deal with at home. So when you're cooking at home, the algorithms and models are like recipes. You can experiment and play around without significant risk. There's nobody looking over your shoulder going, that looks bad. If they are, you can ban them from the kitchen and just keep going. And this is kind of like what we have in research projects. In research projects like experimenting with machine learning, experimenting with facial recognition and natural language processing, we can kind of tinker and we can choose different models and decide what good results actually mean. And often in machine learning, good results means we split our data set into a training set and a testing set. And our model is good if it gets this, it works on the training set after being trained on, on the test set after being trained on the training set. The only problem is the underlying data set we split is all, say, for example, white male faces. Then we train it on white male faces, we test it on white male faces. Oh, good. And it works, but it only works for white male faces. That's all we can say about it from a quality perspective. However, just because you can cook well, just because you're a good cook, it doesn't mean you can run a restaurant. Now, why not? Well, restaurant means you have to cook to spec. You got to make what people want, not what you feel like making. You've got to meet time and cost constraints. People are not going to sit around waiting all day. You can't charge more than you pay for the ingredients. You've got non-functional requirements. Oh, we just had a party of 30 come in. We got to get all these meals out. You've got response times and loading and stress. You have to meet the customer expectations. So in other words, if they look at the menu, they say, well, the menu is hard to read. I don't understand. That's a simple expectation, but you've got to have it. Understanding meeting staff requirements. You got people doing the job. They have requirements as well. There's a whole process going on in the kitchen that has to be managed in order to produce the food, and you got to get it right all of the time. But even if it does fail for some reason, you got to have a contingency plan for what you're going to do when it goes wrong. And the example that I bothered me was when JetBlue introduced facial recognition boarding passes. People said, well, what if it doesn't work? And they said, oh, that's not a problem. Then we'll process you in manually if it doesn't recognize you. Now, as a software tester, that's only half the problem. I'm more concerned about the people that got onto the plane who weren't supposed to get on the plane. What are the contingency plans for those people? I didn't see that. One of the things we know about the industrialized world in every industry is that nothing gets deployed correctly into the real world, correctly meaning it works the way it's supposed to work, without proper testing and quality assurance. Everything, planes, cars, food that you buy in the grocery store, everything is tested. That's why we've got the FDA, and that's why we've got the Health Canada and Agriculture Canada and USDA. There's testing everywhere. EPA, all these kinds of testing. Nothing gets deployed. Even drivers, you can't get a driver's license and drive on the road unless you're tested in order to ensure the quality of what's going on the road. And you're driving a car that's been tested and safety tested. So this notion of testing in QA is pretty ubiquitous throughout our society. And in fact, if you start deploying stuff out into the marketplace without doing any kind of testing, it's at best considered irresponsible and often is considered to be a criminal act. So why do we do that? Why are we deploying facial recognition systems? Why are we deploying Tay the chatbot without doing QA on machine learning applications? The answer is we don't know how yet. Okay, there's the distinction between the stuff that we're deploying that doesn't have, that is in fields that don't have a tradition of testing models. And software testing is in that particular field. Now, Boris Beiser, as I mentioned, was one of the great gurus of software testing. And this was one of the quotes that inspired me when I started getting into the field back in the mid-1980s or early 1980s. It said, more than the act of testing, the act of designing tests is one of the best bug preventers known. And that's very true, because you're constantly asking yourself, what could go wrong? What could happen here? So, we need to design a test because maybe the data is incorrect at this particular point. Maybe this computation fails. So the idea is that forcing yourself to think through the problem from a QA perspective eliminates a lot of problems that may later occur proactively. And so if we had taken the time to design tests for our test data sets in things like the Watson, that question about, oh yeah, there was a problem with how he created the model, that would have been picked up really early in the process before it went out. The question of, well, how is this going to act out in the field? How good does our model, which is a sample of the population, how good is our test training data set as a sample representative of the underlying population? So those questions are the kinds of questions that emerge through this test-first approach that Beiser advocates, and I am a staunch advocate of. In fact, I even take his stronger position, which I adopted, which is if you can't test it, don't build it. And if you don't test it, rip it out. And one of the reasons why that's such an important thing is that the cost of deploying non-tested things out in the world tend to come back and haunt you, often in a very, very unpleasant way. Now, Beiser had basically introduced this notion of these software testing levels, and he said this represents how a software tester tends to grow and mature in the profession. First of all, they start off by doing testing to support debugging. It's broken. We got to find out why it's broken. Then we had a lot of influence from engineering because they had specifications, and we now had software that had to run to spec. And so we started saying, oh, we borrowed ideas from engineering testing of testing to spec. We got to show that the thing does what it's supposed to do. We've also got to show that it's robust enough that it can handle wonky inputs and conditions. I'm going to try and break the data. Now, that worked really well with batch processing, but then we started doing applications where people interacted directly in the 1990s with the internet. And now we had to up our game, which is now generally called agile software testing, is where we improve software quality. It's not just does it do the right job, but it's to do it with all the quality attributes that our users expect. And then finally, level 5 is where you think proactively about constantly trying to identify points of error in the application while you're actually building it. So people who've been involved in Agile are used to these concepts in Agile testing. And there's another thing that we point out is that this is a saying from biology, ontology recapitulates phylogeny. And this basically was the idea that as an embryo is growing in the womb, it recapitulates all the stages of evolution. It gets gills, the gills disappear, it grows a tail, the tail disappears. Biology pretty much has discounted that. But in software testing, the field grew in the same way that Beiser's talking about a tester growing. So we started off with a debugging-oriented period where basically you were looking at the circuits of a computer. Demonstration and destruction-oriented period was where we had a lot of influence into black box testing. By the way, that first period gave us the debugging-oriented period. A lot of the stuff that was done then became what we call white box testing in software testing. The next two periods became black box testing, where you do valid and invalid cases. And then evaluation-oriented period was, well, how did the users like it? We started doing acceptance testing and usability testing and quality measures. You know, is it a good quality software? So, for example, WordStar was the dominant word processing software, but the people that were perfect had a great idea. They said, well, you know what? The users don't know anything about computers. They're mostly secretaries. So they invented something called a tutorial, which would mean no computer knowledge and would take somebody with zero computer knowledge and through a series of lessons guide them into becoming an expert on WordPerfect. So what happened was most people in the field said, oh, come on. A tutorial, get serious. It worked. WordPerfect became the dominant. I think it had about 98% of the market share at one point before Microsoft got into the game. But that's what we talked about, evaluation-oriented period. And prevention-oriented period, this is where we're seeing things in the modern testing world like acceptance, test-driven development, this constant agile DevOps sort of notion of constantly identifying weak places in the software and fixing them before we get into production. So this is right. But now we've got another problem is that all of these ideas are starting to fail with machine learning. So here's the notion of correctness, which was something we're concerned about level 2. If you put into, as Babbage says, if you put into the machine wrong figures, will the right answers come out? People keep asking that. He says, I am not able rightly to apprehend the kind of confusion of ideas that could provoke such a question. And Bertrand Meyer, one of the great software engineers of the 1980s and 90s, said, look, if a system doesn't know what it's supposed to do, then nothing else about it matters. Now, here's the problem, is that that's the basis for a lot of software testing. I know what the result is supposed to be, so I compare what the system does with what it's supposed to be. But we don't know in a lot of machine learning models why or what the correct result should be. So we said they wanted the top 5 resumes at Amazon. Well, what do you mean by top 5? The CV tool. We want to get the best candidate for the job. Well, what do you mean by the best? How do you know somebody's the best? Define best for me. I will give you an example of this. When we were doing machine learning applications, one of the things that we were translating English to French aircraft maintenance manuals, and our funders, several government agencies, said, is the translation correct? What is the percentage of correctness of the translation? And we said, whoa, who knows? So they said, well, we'll get a translator to come in and he'll score it. And we said, well, we'd like to have two translators come in and then we'll average it. And they said, all right. So we got a fellow from Paris and a fellow from Montreal came in. They looked at the machine language translation and the guy from Montreal said, excellent, excellent translation. The guy from Paris said, this is disgusting. It's garbage. Only an uneducated ruffian would even speak like this. And the guy from Montreal said, hey, I speak like that. And he says, yeah, of course, you're an uneducated ruffian. And the guy says, well, you're an elite Euro snob. And we all pretty much had to separate them before the fist fight broke out. So then we had to ask our sponsors, we can't get experts to agree on what a right translation is. So I borrowed an idea from experimental psychology called an operational definition. And I defined what a good translation was for that particular set of aircraft maintenance manuals. And our definition was a translation of an aircraft maintenance manual is correct when you have a French-speaking engineer and an English-speaking engineer, and reading the respective versions of the manuals, they do exactly the same thing. In that case, we deem the translation to be correct. And that's something that we had to do in other social fields when we had to ask things like, what is intelligence? How do we define it? And we have operational definitions of these things. And so again, we take a look at this. What is the right answer? What should it be? Well, we know it's not that your name is Jared and you play lacrosse, but what is it? Well, we don't know. So we've got a problem there trying to apply some of the, when we talk about what is correctness in machine learning, we don't know. Robustness is also a bit of a problem. As you can see, Tay had unintended consequences, became a racist, homophobic, misogynist, and had genocidal and psychopathic tendencies. So, oops, we didn't intend for that to happen. And this is summarized in one of these great memes that came out, this fellow Brennan Keller, who said, correctness, a QA engineer walks into a bar, orders a beer, orders 0 beer, standard, kind of test case modeling, orders 999 beer, orders -1 beer, orders a lizard. Real world robustness, first real customer walks in and asks where the bathroom is, the bar bursts into flames, killing everybody. Oops. That kind of describes, in a kind of an interesting way, a lot of these machine learning to applications when they're deployed. So what we're doing in robustness is asking, so what could possibly go wrong? Boris Beizer's test thinking. And then we start to realize, oh my gosh, that can go wrong. And so we start dealing with these sorts of things. Why is this a concern in particular? Because the U.S. government has just recently proposed that they're going to have AI control nuclear weapons machine learning. Seems like it shouldn't be a bad idea, except for the fact, paragraph 2, you look at there, replete with instances that nuclear war would have started were it not for some flesh and blood human intervening and refusing to begin Armageddon. And there's an example here of Stanislav Petrov, Soviet colonel, who basically saw a launch, picked up a launch of 5 missiles from the U.S. and said, no, can't be true. You'll also notice in 1962, there was a Russian submarine commander who refused to launch a nuclear torpedo that would have triggered war. And also another case that I know of with a Royal Canadian Air Force officer who just died, and I read this in his obituary. There was a chip malfunction at NORAD, and it detected a massive incoming Russian attack, and they had to launch within a few seconds. And he and his American counterpart said, no, this doesn't make sense. And they called one of the forward bases and said, have you just been destroyed by a nuclear missile? And they said, nope. So they said, okay, stand down. Okay, so the question for robustness here is, if you throw these machine learning applications out there, how close are you to triggering a global thermonuclear holocaust? In other words, this is a serious problem. The other problem we have is we don't know what kind of quality people expect from machine learning systems. And what we do know is that quality is not a property of the system. Systems have attributes, and then people interpret that based on their requirements. So, for example, if I ask what's a good quality hamburger, you might say, oh, it's made with Kobe beef and it's got chocolate truffles and it costs $150 per burger. But if you ask a high school student, it's a pound of hamburgers per dollar is quality. They don't care about that other stuff. And here's a typical example of ISO standard 25010, which defines some of the standard kinds of quality attributes that people evaluate their software on. Now we're at that level 4, where we're saying, is the software not just correct and robust, but is it good enough to meet people's expectations and requirements? We don't know about that. And just to give you one small example of that, this is what we call the Uncanny Valley. And this is one of the reasons why those lovely voice systems, you call up a utility company, they go, hi, my name is Bob. I'm a voice-activated assistant. And you say, Bob, I've got an unknown charge on my account. Oh, you want to buy our new special? No, Bob, I want to have a charge on my account. Well, we have you want to add a new phone line? No, I don't want to add. And people would start yelling and screaming at these things because they would sound like just annoying people. And this is called the Uncanny Valley. As things get more and more human, we like them more and more. Human robots are cute, stuffed animals. But then we get to this point where they become very human-like, and we find them creepy because we stop thinking of them as being human-like machines, and we start thinking of them as being people. And when people act the way these very, very human machines do, it creeps us out because they act like defective people. And so this is something about quality. We have to have some way. Notice those voice-activated systems that mimic people aren't around anymore. People hated them so much. There's a quality issue that we haven't begun to really address. All right, so what do? Do we just throw in the towel and say that's it? Not really, because we got a lot of things that we can do to take our software testing to the next level to handle these. What we're really looking at is we're going to have now, since 2019, we're going to have to expand software testing to include the testing of statistical machine learning and even other kinds of models that characterize AI. So throughout history, we have always borrowed techniques. So, for example, our demonstration destruction-oriented period borrowed, I used to say steal, but it's more politically correct to say borrow or adopt the techniques of software engineering, engineering testing. And our evaluation and prevention-oriented period borrowed a lot of techniques from total quality management and industrial control processes, along with quality assurance techniques, given a big boost by the Software Engineering Institute in their process maturity models. And so all of that got incorporated into what we're doing. So what's the next thing we need to incorporate? Well, we're testing statistical models. So we have to define what our tests are measuring. We have to define what it means for tests to pass or fail. We have to figure out how to measure this stuff. We don't want to reinvent the wheel. So does anybody actually do this that we can borrow from? And the answer is yes. There's all kinds of areas. By the way, I'll point out before you get into these other areas that we already do some of this in our experimentation in machine learning. And it's not too hard to modify some of these to become good testing techniques. Data mining has done this for years. Data mining is always worried about things like spurious correlation, where you analyze a data set and you discover a correlation between two things. And I think one of the famous spurious correlations is the number of people dying by drowning in swimming pools versus the number of movies that Nicolas Cage makes. And so no one would suspect that that's a causal relationship. We could stop drowning deaths by locking up Nicolas Cage and preventing him from making movies. But data mining has ways to actually try to say that needs to be tested. So does market research. Market research has found out there's a correlation between men who bought diapers and beer. That was highly correlated, but as it turned out to be just a statistical artifact, when that study was rerun, there was no correlation at all. So in other words, these problems are dealt with in data mining and machine learning to a degree. We also deal with it in social and medical sciences. We have predictive models for epidemiology and other things. Market research, we've been doing this for decades in market research. With surveys are a classic example of a statistical model. It's election time coming up in both Canada and the US. And so polls are out there and we're getting all these predictive models. And there's an example of it right there. Non-functional testing. We don't have right answers in non-functional testing. We have statistical analysis, econometrics. In other words, there's lots of different things, experimental psychology, other things as well. So there's non-functional testing. When we're talking about performance testing, it's not a right or wrong answer. We're testing certain kinds of quantifiable parameters with statistical and confidence intervals and things like that. Medical epidemiology has got something which I tend to use a lot in testing statistical models, which is this notion of sensitivity. How good of my test is at picking up actual faults versus specificity? How good is it picking up only the faults? So something's very sensitive when there's not a lot of false negatives. Something's very specific when there's not a lot of false positives, and very specific when there's not a lot of false negatives. That would be a really good, interesting measure in machine learning, to actually look at how we can score machine learning algorithms based on these kinds of sensitivity and specificity measures. And there's all kinds of, we can do various kinds of predictions as well. Not going to get into it, but this is a really, really interesting and I think fruitful area that software testing can get into involved. So, social network analysis as an application of graph theory. to studying social networks. And when we're talking about various kinds of clustering algorithms, I've often suspected that we can have a very, very rich borrowing of some of their techniques about connectedness and other sorts of issues and apply it to various kinds of clustering algorithms and other kinds of things that we're working with in machine learning. Experimental psychology is very concerned with our models that we're working with very good. So here's some examples of this notion of validity. And I keep on telling my students in software testing, in order to be good, must be valid. It must be valid. It must be accurate, and it must be reliable. And I got that from experimental psychology, which is interested in when we do something like we're going to see whether or not we're going to give somebody a test to determine if they know a particular subject. And so we've got criterion validity. Does this in fact test actually have predictive ability? So, for example, is there some way for us to actually figure out if these resume algorithms that produce top resumes actually correlate with job performance? That would be criterion validity. Content validity. Are you actually testing things that are appropriate to be tested? And then construct validity, which is, are we actually testing what we think we're testing? So, for example, lie detectors fail construct validity because they're not actually testing truthfulness. They're testing physiological arousal. So some of the things that we want to look at here, these ideas can be incorporated quite nicely. Inferential statistics has a large number of ways of testing models. Anybody who's taking courses in inferential statistics knows you've got a lot of these different kinds of samples that we've got, sampling measures and saying, are we really representative of the population? We've got hypothesis testing, type 1 errors, type 2 errors, null hypothesis, reject the null hypothesis. These all can be adapted very easily into machine learning because a lot of them have already been adapted into data mining, which is a very, very close cousin to machine learning. And again, machine learning is basically statistic modeling. Now we've got these testing techniques we can apply. Here's another field, econometrics, which creates econometric models and then has a number of ways to test them to see if they have validity, to see if they have predictive capabilities. And there's one just grabbing from this one from Introductory Econometrics for Finance called the Goldfield Quant Test, which is another example of determining a formal test. So all these fields have these techniques. Remember, we looked earlier at machine learning that actually works well in production because it's deployed into fields that have these kinds of techniques. So we need to be able to test and do quality assurance of machine learning applications. Software testing as a formal science does not have those techniques yet, but typically and historically, we adopt techniques that we don't have and we need from fields that are doing it. And that's how we respond to new challenges. And other disciplines do right now have exactly the tools that we need. So as software testers, what we're doing, we are going to improvise. We're going to use what's available. We're not going to reinvent the wheel. We have to meet this particular challenge. So we borrow or steal these techniques from other areas. Then we adapt them to the quality or the methodologies that we use in software testing. So we borrow these techniques, but then we turn them into our software testing methods, which should be a lot more rigorous than maybe in some of the other fields. And that allows us then to be able to test machine learning applications and avoid the kinds of embarrassing situations that we saw at the beginning of this presentation. So my final statement on this is that software testing is faced with a challenge, and I think software testing is ideally suited to be able to meet that challenge, and that will benefit both the field of software testing and help the machine learning to make those kinds of inroads that it seems to be stymied in some areas of making. All right, and after that, so Tim, I'll turn it over to you for questions.
Thank you, Rod. We do have a few, and they can continue to come in as we dialogue back and forth with these questions. Do not hesitate to fire more in. First question, Rod, why not just use an agile or DevOps approach and deploy the application, get feedback, and tweak the machine learning model based on that?
As a matter of fact, the agile and DevOps models are more about production processes, but they do stress constant testing. And so if you're agile testing and testing in DevOps, you're in Beiser's levels, you're working at levels 4 and 5. But in order to do that, you have to have the various techniques, which you have test-driven development, acceptance test-driven development, exploratory testing. But the problem is not in how we're organizing or going about our testing. The problem is we're lacking still the proper tests for the thing that we're testing. Okay, so in other words, if you were going to test for temperature, but the only thing you had was a scale, it doesn't matter how good you try to organize your testing, you can't test temperature with the scale, and you can't test weight with a thermometer. So we really have to add this set of actual measurement tools to it, and then it can be applied again in DevOps. And I personally think that the DevOps and Agile approach gives us some really good models for thinking about how we can do this kind of work with machine learning as well in terms of the framework, but the tools we're still missing.
Okay, excellent. Thank you. Sorry I interrupted you there. I thought you were done.
No problem.
Currently, I have two more questions. If a lot of these fields already do testing that works for machine learning, for example, medicine and engineering, why do we need to duplicate this in the software testing field?
The answer for that is that their tools are often specific to their field. And so while they're for example, if you look at econometrics, their tests are specifically geared towards financial models and finance models, which means that, of course, that FinCEN, the people looking for money laundering, are able to use those techniques for testing their machine learning models quite well. So the problem is twofold. Number one, we've got to adapt those techniques from the specific applications or specific fields they're developed in and make them more general. But the second reason is that software testing also has a number of protocols, software testing protocols that have to be followed, and they have to be adapted to those protocols, because while other fields do have protocols, they're not always the same as software testing. So in other words, we have to not only ensure that we've got the tests, but we are able to administer the tests in a correct manner to reduce the problem of mistesting, bad test results.
Okay, excellent. Thank you. I have another one in, so I again have two questions left. Black box or functional testing is done without knowing anything about the structure of the system under test. Why isn't it good enough for machine learning applications? Why not just treat them as black box?
The answer to that is that black box testing is predicated on the idea that we already know in advance what the right answers are, and we don't need to know anything about the underlying system to be able to examine the answers it spits out and compare them to what we expect and say, okay, it got that one right, it got that one wrong. But if we go back and we look at the example of the resume where it was Jared and playing lacrosse were spit out as the answers, the problem is that we know that's wrong, but we have no idea what the right answer would be. So all we know is if we got an answer saying it was a particular SAT score in English and maybe somebody who worked part-time, that makes sense, but is that really the right answer? So the problem with black box testing and machine learning is that in black box testing, you have to know before you test what the right answer is going to be. We don't know in machine learning, so that means we can't really use that kind of testing.
Okay, and my currently last question is, what approaches can be applied for automation testing?
Well, by this, I'm assuming we're talking about something like automation testing. Let's suppose we're putting into place a loans approval system. We're replacing our loans officer with a loans approval system. And we've trained it on a bunch of historical data. And that historical data reflects the decisions that loans officers have made in the past. And well, actually, let's not do it. Let's do sentencing, jail sentencing, because that actually has been studied. The problem with if we develop a system to decide what sentences should be for criminals in the criminal justice system, that system actually went into production and it was trained on historical data, which was racist. And so the system started making racist judgments. So the problem is that the system may be consistent with historical techniques, but we want to know, is it consistent with, from a quality perspective, the kinds of decisions people make it today? So one of the ways that we can do this is use what we call correlational measures. In other words, we can look at people who are now doing sentencing the way we think it should be done or the way we think is correct, and have the machine learning also, the system also do the sentencing for the same cases, and then compare them to see how well they correlate. If the machine learning system starts to be able to make the same kinds of decisions that a group of experts would in the field, then we would say, okay, this machine learning system isn't doing too bad. If the machine learning system starts to get really have a lot of variance from these experts, we would say, okay, so maybe it's the training data, but it's not doing what people are expecting it to do. And by the way, just as a point, there is one technique that's kind of used for that machine learning, which is called the random forest, which also has a sort of idea built into it. So anybody who knows what random forest is, you're already seeing a little bit of that model creeping into machine learning. But the idea here is that by correlating it with people who are doing it in what we consider to be the correct way, we're able to start working to see if we're getting answers that meet people's quality criteria for, oh, that's a good answer, or that's a good result, or that's a good sentence.
Okay. No new questions have come in, so we are out of questions. Any last comments from you, Rod?
No, I think that this is going to be an exciting area for people in software testing, machine learning, to start to collaborate. And I think that we've got some really positive things that we can see coming out over the next while if we start doing these things.
Excellent. And again, appreciate your time, Rod, your expertise in delivering this. Everybody that came, thank you very much for attending. If you'd like to delve a little bit deeper into any of this, we do have courses coming up in our future on software testing functional techniques, effective methods of software testing, agile testing and software quality, and managing software testing and quality assurance. Additionally, off of our resource page, there are webinars past and future. You might want to keep an eye out there as well. Thank you again, everybody, for coming. It is greatly appreciated. Have a great day.